When people hear about overheating locomotives, they typically picture a steam engine running low on water or a diesel with a failed radiator sitting dead on the tracks. But electrification presented railroad engineers with something they hadn't anticipated. The heat problem didn't disappear with the smoke. It simply moved somewhere else. The New York, New Haven, and Hartford Railroad, known simply as the New Haven, pioneered high-voltage alternating current electrification in America. Their solution to the smoke and congestion problems of the early 20th century was elegant and forward-thinking, but it came with challenges that the engineers of 1907 never fully anticipated, challenges that would shape how railroads thought about thermal management for generations. This is not a story about locomotives that overheated. It's a story about what happens when you move millions of watts of electrical power through confined spaces, when you eliminate one form of pollution only to discover you've created another, and when the infrastructure built to solve yesterday's problems struggles to handle tomorrow's demands. Grand Central. The name evokes grandeur, architectural magnificence, the very essence of American railroad ambition. But in 1900, the original Grand Central Depot was choking on its own success. Steam locomotives by the dozen crowded into the Park Avenue approach, their smoke and cinders filling the tunnel that led into Manhattan. The air in that tunnel grew so thick that engineers could barely see their signals. Passengers complained of the suffocating heat, the soot that covered their clothes, the acrid smell that permeated every car. On January 8, 1902, the inevitable happened. A southbound express from White Plains entered the smoke-filled tunnel, its engineer unable to see the signals ahead. He plowed into the rear of a waiting commuter train from Danbury, Connecticut. The collision killed 15 people and injured more than 30 others. The boiler of the express locomotive tore through the last car of the stationary train, spewing steam and burning coals among the passengers. Public outrage was immediate. By 1903, New York State had passed legislation banning steam locomotives from Manhattan south of the Harlem River, effective July 1, 1908. The New York Central, which owned Grand Central, had no choice but to electrify. Neither did the New Haven, whose trains shared the same tracks into the terminal. But while the New York Central chose a relatively simple 1660-volt direct current third rail system for its portion of the route, the New Haven faced a different challenge. Their main line extended 72 miles from New York to New Haven, Connecticut. Direct current loses voltage over distance, requiring substations every few miles. For a long-distance operation, this was impractical. The New Haven needed something different. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. Working with Westinghouse Electric, the New Haven's engineers developed a solution that would become the standard for heavy-duty railroad electrification worldwide: high-voltage alternating current. 11,000 volts at 25 cycles per second, delivered through overhead catenary wires, with locomotives capable of drawing power from both this AC system and the New York Central's third rail DC system within the city limits. The technical achievement cannot be overstated. In 1907, when the first New Haven electric trains ran into Grand Central, there was no precedent for this kind of mainline electrification anywhere in the world. The Baltimore and Ohio had electrified its Howard Street Tunnel in 1895, but that was a mere 4 miles of track. The New Haven was building something on an entirely different scale. At Coscob, Connecticut, on the banks of the Miamis River, Westinghouse constructed a dedicated power station in the Spanish Mission style. The plant's coal-fired steam turbines drove 3-phase alternators that supplied single-phase power directly to the catenary. It was the first power plant in America built exclusively for a railroad, and it would serve the New Haven and its successors until 1986. The system was designated a historic mechanical engineering landmark by the American Society of Mechanical Engineers in 1982, recognition of its enormous influence on subsequent electrification projects. The Pennsylvania Railroad studied the New Haven's work closely when planning their own electrification, and the basic principles established along the shoreline would eventually be adopted from Washington to Boston. The first generation of New Haven electrics were the EP1 class, delivered by Baldwin Westinghouse between 1905 and 1908. These box cab locomotives were engineering marvels of their day, equipped with both pantographs for collecting AC power from the overhead wire and contact shoes for the DC third rail. They could transition between the two power systems at track speed without stopping, a necessity given the volume of traffic on the approach to Grand Central. 41 EP1s entered service, followed by 27 EP2s delivered between 1919 and 1927. These were enlarged versions of the original design, producing roughly 2,000 horsepower and capable of speeds up to 70 miles per hour. They handled the bulk of passenger service for nearly 3 decades. In 1931, General Electric delivered 10 EP3 class locomotives. These represented a significant advancement. Their 2 to C plus C2 wheel arrangement, with 2 pilot axles supporting 3 powered axles on each of 2 articulated trucks, provided excellent tracking characteristics at high speed. The EP3s used a twin quill drive system, with each of the 6 driving axles surrounded by a hollow shaft, connected to the traction motors through large gears. This arrangement reduced unsprung weight and improved ride quality. The Pennsylvania Railroad borrowed EP3 number 0354 for testing at their facility in Claymont, Delaware. The locomotive's performance so impressed PRR engineers that they adopted the same basic mechanical design for their legendary GG1 class. That connection is sometimes overlooked today, but the iconic GG1, perhaps the most recognized American electric locomotive ever built, owes its fundamental architecture to this relatively plain New Haven box cab. In 1938, 6 EP4 class locomotives arrived from General Electric's Erie, Pennsylvania plant. These were streamlined units with a modern appearance, their car bodies styled in the fashion of contemporary diesel locomotives. They delivered 3,600 horsepower continuously and could produce up to 7,600 horsepower for short bursts of acceleration. The EP4s were geared for 93 miles per hour and regularly handled 15-car commuter trains into Grand Central and 20-car express. Trains into Penn Station. Here is where the story takes its turn. Steam locomotives generated enormous heat. That was obvious to anyone who stood near one. But that heat dissipated into the atmosphere. The fire, the steam, the exhaust all released their thermal energy into the open air. Even in tunnels, the movement of trains created enough airflow to eventually clear the heat along with the smoke. Electric locomotives operate differently. The conversion of electrical energy to mechanical motion is remarkably efficient compared to steam, typically around 90% or better. But that remaining percentage has to go somewhere. Add in the heat generated by braking, by the friction of wheels on rails, by the electrical resistance in the motors and transformers, and you have a significant thermal load that doesn't simply blow away in the exhaust. In open air, this was never a problem. Electric locomotives ran cooler than their steam predecessors, and the ambient environment absorbed whatever heat they did produce. But in enclosed spaces, in tunnels and covered terminals and underground substations, that heat began to accumulate. Grand Central Terminal, when it opened in 1913, was an engineering marvel. 2 levels of tracks, 44 platforms, all buried beneath the streets of Manhattan. The designers had carefully planned for ventilation. The movement of trains through the close-fitting tunnels acted as a piston system, pushing air through the station and out to the surface through sidewalk gratings and vertical shafts. During the construction of Grand Central, engineers debated whether to waterproof the entire structure. They ultimately decided against it in some areas, reasoning that allowing heat to dissipate into the surrounding earth would help keep temperatures manageable. In the original 1913 design drawings, engineers proposed heating, ventilating, and evaporative air systems to condition the main concourse. These were never installed, what we might today call value engineered out. The natural airflow from train movements was expected to suffice. For decades, it largely did. But as traffic increased, as trains grew longer and more frequent, as the electrical systems expanded, the thermal load grew with them. The tunnels that had once been refreshingly cool compared to the smoke-choked approaches of the steam era gradually warmed. Today, anyone who has waited on a Grand Central platform in summer knows that the underground portions of the terminal can become uncomfortably hot, particularly during heavy traffic periods. The heat management challenge became most acute with the New Haven's final class of electric passenger locomotives, the EP5s delivered by General Electric in 1955 and 1956. These 10 locomotives, nicknamed Jets for their distinctive sound, represented the cutting edge of 1950s electric traction technology. They were the first production locomotives to use ignitron mercury arc rectifiers to convert the 11,000-volt AC from the overhead wire to direct current for the traction motors. This eliminated the need for heavy motor generator sets, saving weight and improving efficiency. The EP5s packed 4,000 horsepower, more than any previous New Haven electric, into a double-ended carbide. They could collect power from both the AC catenary and the DC third rail. They could operate in either direction without turning, and they carried the Pennsylvania Railroad's cab signaling system for operation through Penn Station. They were supremely capable machines, but all that equipment generated heat. The transformer stepped down voltage, creating heat. The ignitron rectifiers converted AC to DC, creating heat. The 6 DC traction motors drove the wheels, creating heat. The resistance banks used for DC operation created more heat still. And unlike the earlier box cabs with their relatively spacious interiors, the EP5s stuffed all of this into a tightly packed body that left little room for airflow. Contemporary accounts describe the EP5's ventilation blowers as remarkably loud. When these locomotives passed through stations or sat on platforms, passengers and staff alike noticed the noise of their cooling systems working at full capacity. In the Park Avenue tunnels approaching Grand Central, where ambient temperatures could already be elevated, the EP5s worked their cooling equipment hard. Several sources note that these locomotives had a tendency to overheat, especially in the Park Avenue tunnels under Manhattan. Later modifications added ventilation grills to the locomotive's sides, installed after several thermal-related incidents. The contrast is visible in photographs from different periods. Early images show relatively smooth body sides, while later shots reveal additional openings cut into the sheet metal to improve airflow. The locomotives were only part of the thermal equation. The infrastructure that supplied them with power generated its own significant heat load. Along the New Haven's electrified territory, substations stepped down voltage from the transmission lines and converted it for use by the catenary. These facilities contained transformers, rectifiers, switchgear, and control equipment, all of which produced heat during normal operation. Many of these substations were built into urban environments where space was at a premium and ventilation was limited. The M42 sub-basement beneath Grand Central Terminal housed the rotary converters that supplied DC power to the New York Central's third rail system. This facility, whose precise location was deliberately omitted from building plans, contained massive electrical equipment that required constant cooling. Ventilating fans circulated air through the space, with exhaust routed through the Grand Hyatt Hotel's smokestack. In the tunnels themselves, the catenary's supply and return circuits carried enormous currents. Every electrical connection, every joint in the wire, every contact between pantograph and trolley wire represented a point of resistance, and resistance creates heat. The cumulative effect across miles of wire was measurable. The substations at Cos Cob, Stamford, New Rochelle, and points between all faced cooling challenges that the original designers had not fully anticipated. Over the decades, fans were added, operating limits were adjusted, and cooling systems were upgraded. The 1913-era assumption that natural ventilation would suffice gave way to an understanding that active thermal management was essential. The crews who operated the New Haven's electrics developed informal rules for managing heat. In summer, power consumption limits were sometimes imposed in the terminal areas. Trains might be held at outer stations rather than queuing in the tunnel approaches. The timing of heavy traffic movements was coordinated to avoid having too many locomotives idling in confined spaces simultaneously. The EP5s, with their known thermal sensitivity, were monitored more closely than other classes. Dispatchers learned which assignments were most demanding and which locomotives were best suited for tunnel-heavy runs. This kind of operational adaptation, where human judgment compensated for engineering limitations, was typical of mid-century railroading. Passengers noticed, too. The platforms at Grand Central could become noticeably warmer during rush hour than during lighter traffic periods. In summer, the effect was amplified. The waterproofing that engineers had debated in 1913 did prevent water intrusion, but it also trapped the heat generated by train movements, preventing its dissipation into the surrounding earth. Some reports from the construction of subsequent subway lines noted the elevated soil temperatures near the Grand Central tunnels, evidence of decades of accumulated thermal load. The New Haven's experience illustrated a principle that would become fundamental to electric traction engineering. Thermal management cannot be an afterthought. Steam locomotives had been inefficient, dirty, and labor-intensive. But they had one virtue from a thermal standpoint. Their waste heat dissipated naturally with their exhaust. Electric traction eliminated the smoke, eliminated the ash, eliminated the water stops, and the coaling facilities and the army of workers needed to service a steam fleet. It was cleaner, faster, more efficient in almost every measurable way. But the energy that wasn't converted to useful work still had to go somewhere. Early electric railroads assumed that the efficiency gains meant less total heat to manage. What they discovered was that concentrated power in enclosed spaces could create thermal accumulation that steam locomotives never had. Modern electric railroads incorporate this understanding from the design stage. Tunnel ventilation is calculated based on traffic density and locomotive power ratings. Substations include active cooling systems sized for peak loads. Rolling stock is designed with thermal limits defined and monitored. Regenerative braking, which converts stopping energy back into electricity rather than dissipating it as heat in brake resistors, has become standard on many systems, particularly those with heavy stop-start service. The London Underground, which pioneered electric underground railways, has struggled with tunnel temperatures since its conversion from steam in the 1890s. When the Bakerloo line opened in 1906, it was advertised with a maximum temperature of 60 degrees Fahrenheit. Over time, the tube tunnels have warmed substantially. Temperatures exceeding 117 degrees Fahrenheit were recorded during the 2006 European heat wave. The London system's experience mirrors the lessons learned at Grand Central and along the New Haven, scaled to an even larger network. The New Haven Railroad entered bankruptcy in 1961, victim of competition from automobiles and airlines, mismanagement, and the declining fortunes of the New England economy. Its electric operations continued, but investment dried up. The EP5s, for all their sophistication, saw only about a decade of service under New Haven ownership before the railroad was absorbed into Penn Central in 1968. Under Penn Central, the former New Haven Electrics were redesignated. The EP5s became E40s. Several were retrofitted for freight service. The fleet soldiered on through Penn Central's own bankruptcy, through the creation of Conrail in 1976, through the transfer of commuter operations to Metro North in 1983. The catenary that Westinghouse energized in 1907 still carries trains today. Metro North's New Haven line runs electric multiple-unit cars over the same route, serving commuters just as the New Haven did more than a century ago. The system has been upgraded, of course. The 25-cycle power that the original generators produced has given way to modern frequency standards. New substations have replaced the aging infrastructure. Air conditioning on the trains themselves has transformed the passenger experience, but the fundamental challenges remain. Move enough electrical power through confined spaces, run enough trains through tunnels and terminals, and heat will accumulate. The engineers of 1907 discovered this gradually through experience and adaptation. Their successors have built on that knowledge, designing systems that account for thermal loads from the beginning.